Hello. Does it turn on? Hello. Hello. Hello everyone. Good evening. Thank you for having me a second time here at LivePerson at this event. Very happy to be here again. So tonight I have so it looks a bit static, but I have to stay here, otherwise you won't hear me. Stop it. First of all, we have these great balls here, like LivePerson organized those, and I think I will use those if I find anyone falling asleep. I start throwing them, so careful. Just kidding. And the talk tonight is about HBase and Hadoop and real-time analytics. So let's get started. Let's turn this around. Right. So, quick start about me. I'm a solution architect at Cloudera. I'm the EMEA representation of Cloudera, so I'm traveling from far and abroad. I go to Israel, all the way to England, all the way down to Italy, and I have worked with customers in Norway, so I span, I think, the majority of Europe. And I'm also a HBase and React committer, so I'm having a developer background, but as I said, I'm more like a solution architect today, so I'm splitting my time between doing actually engineering work and helping other people to use the software I work on to be successful, which is a couple of companies here in Israel as well. I'm also the author, if anyone is interested, of O'Reilly's upcoming HBase The Definitive Guide, which covers everything that you didn't know before about HBase, I hope. So if you're interested, please have a look out, have a look for that on Amazon or wherever you want to. So, okay, let's start with the sort of the application stack. The idea I had when we talk about real-time and Hadoop and then HBase and throw this into the mix, it's sort of like, for me, a look back of what happened over the last couple of years. So initially, we were like providing software without any sort of schema or plan. We just throw things together, wrote it from scratch. There was no sort of anything default that we could use. And over time, we had the application stack developing, which gave us certain parameters, certainly some restrictions, but we got something we could build productive or business applications on. So these solve our business goals. That's the outset. Otherwise, we don't need those application stacks. And let's do it this way. We rely on proven building blocks. So the idea is that we don't go out and rebuild and reinvent the wheel and build systems over and over again. You suddenly have something that you can reuse over and over with changing needs for your business goals, but they're also very similar in certain ways. So that's a good thing. Also, they allow us to do rapid prototyping. We have something that we can build, set up in a few minutes because we know it already. We throw in the business logic and we can see how the thing goes or how it develops. So that's important. It comes with these model view controller ideas, reference implementations you can look at, like the Java Enterprise Edition comes with these pet store or something you can look at and learn from it and then make use of it. Is that okay? Sorry. Better this way. Okay, all right. Is that better? Everyone can hear me? You can hear me? Off here? All good? Not so good. If I speak up, is that better? Or does it? It's okay? I try to be loud, but it gives this feedback. So with this application stack, we got something that goes into this discussion of revolutionary creation, evolutionary, but for me it's basically evolutionary cycles. So we see innovation happening in cycles. So something, you have an application stack and we add to it, and we add to it, and it helps us solving new problems. So the idea is we need some sort of light that helps us in the dark, and that's basically being the lamp. Obviously, that's not the lamp that you have in your room or in your desk, but it's the LAMP stack. So the idea is that you have Linux as the operating system back then. Everybody see? Linux as the operating system. We have Apache or any other web server that serves the web requests. Then we have MySQL as a database, and we have PHP or Perl to develop. That was sort of like the first application stack that came out that was for free. We didn't have to pay for anything, and we could build something very quickly. You could prototype, throw it away because it didn't cost any money. So that's quite interesting, and it's good. The next step after doing this, you realize that as you grow, as your traffic to your website increases, you realize that you have maybe not enough capacity with your servers. You can add more servers maybe, or you can somehow make, I don't know, use of other optimizations, reduce certain things that you thought were great, but they aren't in terms of performance. So the next logical step is you add memcache. So memcache basically is the next layer up on top. So from that LAMP stack, we get that LAMP stack, which is like everything we knew before, but we added a caching layer, right? So that's sort of the next step. And then, of course, the big thing strikes, because all of a sudden, this little memcache that you have and your few servers aren't going to cut it anymore. So suddenly, we deal with what basically is coined the big data age, or we don't want to use any other metaphors there. There's a lot of talk about this. Everyone who sits in here who heard about and works with Hadoop knows what I am talking about. This includes not just the typical web properties like Facebook. Everyone knows Facebook. We know eBay and all of the other companies who collect a tremendous amount of data, but they're also the brick and mortar companies. Be it power companies who have these sensors on the grid to determine what's going on and detect failures and things like this. We have the financial companies who just have stock tickers and want to analyze that. So data comes in all the time. It came in before as well, but often that data was just thrown away, or it was kept for a certain amount of days. But after that, it was just thrown away because we couldn't retain it. You may be able to aggregate this and save some summary so you can actually make use of it, but you cannot really look at the original data and change your model in 3 months' time because you have already thrown away the original data, so what you computed is static and you cannot derive the original data from it. So that's basically your start. So as soon as you realize that you're throwing away data and these other companies that suddenly store all their data and make use of it makes them more successful, you have to realize that you have to do the same thing. It's just a natural progression. We back into this evolutionary step. You realize, okay, they do it, I do it as well, so we have to go there as well. We just have to do that step and collect all that data. Then you have all of a sudden these algorithms that you can use on all your data that actually generates more data. So this just compounds to it. You use machine learning algorithms and you add to it, and like the explosion of the data is just tremendous. You have to store them somewhere, and out of that data you can derive new data, and so on and so forth. So this is not going to end. It's not going to go away. We will just have more and more data that we have to store. Previously, as I said, we might have had the chance to collect as well a lot of data, but there was no way to really handle this properly. So there was sort of a lot of loss, and we cannot go back, but we can go forward. Also, what was this paper? There's this paper from some of the Google fellow engineers. Google fellows, they have this paper out which is called the unreasonable effectiveness of data, which says the more data you collect, the simpler the algorithms can be, and you can actually make more sense out of it. So collect a lot, simplify your algorithms so you can crunch through quicker, and you will see that for some reason it's like statistics is a great thing, math. It brings us closer to the goal that we wanted to go. So that's all like adding to this problem. And out of nowhere, a few years ago, we had Hadoop. Hadoop came to solve a big data problem, but quickly, obviously, open up its doors to all sorts of applications. It's based on the Google papers that were described. They came out in 2003, 2004, describing a file system that could store all that data and a computational framework that you could use to crunch all that data into reasonable or into effective data at the end. It's a distributed storage and computation framework. It runs on affordable hardware, and it's free. Like the software on top of that is free. So all you have to invest are the servers. It's a great proposition. And there's a significant adoption of Hadoop in the market. I mean, Facebook, eBay, Yahoo, anything you can, any sort of web property of scale uses Hadoop. And lots of brick and mortar companies, banks that we personally know about. We have a lot of customers, not just in the web properties, but traditional businesses which deal with a lot of data. They are part of the adopters for Hadoop. So Hadoop is nowadays, it's a difficult term nowadays. Hadoop, I think, is more like an ecosystem. Hadoop has a lot of components in it. But primarily, if someone says, oh, I have a Hadoop cluster, what they usually mean is they have HDFS and MapReduce. These are the two sort of things that they are part and parcel of Hadoop. Nowadays, if we as Cloudera, think about Hadoop, it's like an ecosystem. It includes Hive, Pig, HBase, Flume, a lot of other things that Uzi, there's a lot of other things that you can think of or that you can name that we think is all part of this whole package. HDFS gives us the storage. It's this open source implementation of GFS, so you can store a tremendous amount of data in on these cheap nodes. Right? So you can scale to thousands of nodes and just store whatever amount of data you want. And that's great. So it's all like stored, whatever you had to throw away previously can now be stored reliably and on quite cheap hardware. No filer, no RAID, no expensive SCSI disks or whatever. You just go cheap, and wherever you want to start, you can go you can go with a cluster that a normal database server probably even doesn't get you. So you can, like, with a reasonable amount of money, start your own Hadoop cluster. That's really interesting.
People saying they can't see the presentation.
Oh, I can move over this way, right?
Pick it up.
Okay, let's try this. Oh.
You want to take all this?
And yeah, but then I block these guys. So maybe I move around. Is that okay?
What do you want to?
It doesn't. Yeah, let me see if that works. Yeah, well, let's try this here. Okay, so I move around. I can't go too far because of that microphone, so I'm wired. Let's go over here. Let me know. Is that okay? Can you see? Good? You can see. All right, so thank you. Let's do it this way. So HDFS gives us this, the storage. The next thing is MapReduce. I mean, I'm repeating this a bit, and you already know all that, but it forms the basis of what comes after. So I think it's an important start to sort of recap where we add with Hadoop. So MapReduce gives us the distributed programming model. So it gives us uses the CPUs that we have already in the storage layer. All of these machines that we use to store all this vast amount of data have CPUs. So why not make use of them and crunch some numbers? And that's what MapReduce does. It's also important that if you want to process data, you don't want to shift this around. If you look at the layers in your network, if you look at the layers in your setup, the quickest one you have, or the fastest one you have available, is memory, or CPU and registers. Then you have memory, and then you have the disks, and then you have the networking. So if you can skip a layer, not using something that is slower, but can use something that it can move data or do stuff faster than a layer below, then you should make use of it, because then you get a much better performance. So this is basically the idea here with locality. The idea is that you bring the code to where the data resides. So you're writing code, it gets shipped, the small bit of code gets shipped to all of the servers, and they run in parallel all of the analytic tasks they have to perform. And it runs in parallel, it gets aggregated. So that's a really good way of just using the data that is stored local on disk, as opposed to taking the data, shifting it over. Because we had this in the past, this sort of like moving things around to where things are computed. So you have like a central node that does like some computation and goes over the network and gets the data. We had this for years. This is about reshipping the code. The code only talks to the data which is local to its node. And therefore, you're skipping the whole networking. You're only going through what is stored locally, analyze it, and ship the results back. The idea of MapReduce is also that you don't output the entire thing at the end, ideally, but you reduce it. The idea is you extract something from the data, that's the mapping part, and with the extracted information, you reduce that information to something even less. So for example, you have address records in HDFS. You could go over and only extract, for instance, the street. And then you can use that street and then do a count of how many streets you have in a certain vicinity. So you bring it down to a number. So the end result is much, much slower. And you're only bound by disk I/O. That's important as well for scalability when we get to the next stage. So it does this input, it maps, it copies sort, I didn't mention this before, as a node sort of finishes its mapping phase, like extracting the street from the address, it has to then send this to a central, somewhere to another node, which then aggregates all of the same streets to do the right computation. That's called the reduce step. But for the reduce, there is some networking involved, which is this copy and sort. But if you do the mapping right, you're only transporting a subset of the data across the network. And if you do the computation, or if you design the job right, you can minimize how much is actually being transported as well. But bottom line is there's some sort of sorting so that the reducer sees all the streets that are the same and can then count how many it has seen. So that's basically sort of the whole MapReduce phase, fairly straightforward. So okay, we were talking about the LAMP stack, right, and Hadoop. So what is the next logical step? The next logical step is you combine both. I mean, it's fairly straightforward. If you look at certain products in the IT world, this is back to this evolutionary step. It just gets reused, combined, thrown into the same pot, mixed up. But in the end, it's exactly this. It's the same tools, just used slightly differently, and it makes sense. So here we have, I have this. I have the LAMP with the memcache in between. There's a wedged in between here, and we have, which basically serves the client, right? That's the web layer. So this is the application layer, stores the intermediate data. It talks to you when you basically go to your bank and do online banking. That's that sort of layer. And no matter how old this is, this whole LAMP stack, if you look at Facebook, and we get back to that, they still use the LAMP stack. So it's not like it's outdated or so, it's just evolved into something else. And then we add this sort of Hadoop layer, right? We just plug it in and say, okay, there's Hadoop. So we make use of it. And how? For long term, we store the background information for long-term storage, and we use background batch processing to do the analytic part, like the analysis of the data, the computational part. You just basically have the front-end layer writing into the back-end layer, which is like the LAMP giving the data to Hadoop, and then you do the analysis whenever you want to. And you can feedback, so this is like a bi-directional way, so the LAMP stack can say, okay, the computation is done, so how many streets do I have in this vicinity? Give me that number, and when the customer gets the report, there is the number, right? So it's a straightforward process. The next step is, what does batch processing really entail? Sure, which is great. The scale is unlimited, which means you can suddenly store lots of data, and you can process this data. It's different to what you have seen maybe in past implementations where you use one machine which goes to the data and does the computation. This case here, it's designed in a way that you never run out of memory. So you can have machines which only have, I don't know, like 4 gigs of RAM, which is really small. I mean, all of your notebooks probably have already 4 gig of RAM, or 2 at least. So this is really, for server side, this is really minute, and still it's enough for Hadoop to do its job. So it's bound here only by that number of the hardware. So if you add more nodes, you get more parallelization, and you can process more data. And the tremendous effect, or the tremendous advantage of Hadoop over anything else, is that if you double your capacity, you get double the computation power, you get double the storage, and it's really as linear as you can think of it. It's really that if you have a job that runs, say, on 100 nodes in 10 minutes, if you double to 200 nodes, it runs in 5 minutes. So it's really great. So you can rely on that. If you add 10 more machines, you get 10% more improvement, or you can do nice planning, which is a great advantage as well. So if your job runs too slow, you just add more hardware, right? That's just like as easy as that. You harness the power of the cluster, the CPUs, the disk, the memory. What I mentioned is why you never run out of memory is what is called a spill. So the idea here is that as you process, or as these nodes process your data, if you run out of a certain amount of data, like a certain amount of memory, it just takes that and writes it to disk. Sure, again, we are moving from one layer, from a faster layer to a slower layer. So we're going from memory to disk. But it doesn't matter, because in this case we want to have this job finished as fast as possible. So it's better to go to disk as running out of memory and stopping the whole thing. I've seen this in the past where companies would have a beefy machine which does some processing, and it worked fine, right? So it does the computation, and all of a sudden you sort of ramp up your traffic, and this computation goes from say a couple of minutes a day to like a few hours a day. All of a sudden you break the 12-hour barrier, which means you're already taking half a day to process the data from the day before. We talk about like a day's worth of data. And as you further grow, you're approaching 23 hours, and then you're hitting the 24 hours, and then you basically need as long to process the data as what you collect in one day, and you're done. That's it. You can add maybe another machine, but how do you, there's no, all you do afterwards is your own job, because how do you aggregate the data at the end, and how do you scale this? There's no support for that. And what usually happens, and I've seen this many times in practice, is you start sampling. Oh, it's easy, you know, you just add a little bit of error. So just don't go to every record, go to every third record. Gives us a good sampling rate. So you reduce what you're actually looking at, and at the end, you're basically having some error rate over some sort of amount of data, and you're still not really keeping up with the growth. So the idea here is these spills are a good thing. You want to maintain them at a certain rate, so you can tweak this with Hadoop. But they basically give you this extensibility into whatever the capacity of your disk is. If you exceed the space of your disk, go figure, you add more nodes. That's as easy as that. You just basically divide and conquer. If you exceed, add more nodes. If you exceed, add more nodes. And you can do it. If you're too slow, add more nodes. So it just goes like that. You trade, though, the size limitations for time. So, as I said, a job takes time. So we are talking batch processing, right? We are going now the next step. So what I see in practice is companies looking at adding Hadoop to their stack. Typical, like as a LAMP stack, adding Hadoop. This happens many, many times. And all of a sudden, what they needed 23 hours for to compute, or like even close to 24 hours to compute last day's worth of data, to give you something like 24 hours later, you've got the updates to your customers to see, I don't know, some calculated data. They bring this down with Hadoop by a huge factor. All of a sudden, that same job takes 30 minutes. Wow. I mean, all of a sudden, 30 minutes before it was like 23 hours. How can this happen? And we just had like 10 nodes before I had this one beefy one, and now that doesn't make sense. Even if I divide by 10, it shouldn't be as fast as, it shouldn't be like 30 minutes compared to 23 hours, but that's actually the reality. These MapReduce jobs work so efficiently, not copying data, that you save so much along the way that this job tremendously improves, right? That's great. And you keep going, right? This, like, you just add more users and everything, and I mean, your management, they are like thrilled, absolutely excited. You broke the sound barrier. You went from 23 hours to 30 minutes. That's like near real time, right? This is like, wow, 30 minutes, great. And go figure again, a couple of months down the road, your management comes to you and says, you know what? Can't we make this faster? I mean, there's like 30 minutes is great, you know, but how about 5 minutes? Like, I mean, that would be great, right? Because then we can like deliver something our competitors can't. We can go to like 5 minutes. It's like nearly real time. I mean, it's like, wow. So time is money. That's basically sort of it will happen to you. It happened to a lot of people that you get pressure to do it faster. First step is obvious, add more machines. I mentioned that, I think, a few times. So you're adding more machines, you bring down the time, but at some stage you're ending up at a low point. You cannot make a batch job run faster than, say, 2 minutes, minute and a half or so. I mean, there were many discussions on the mailing list about maybe we can make it so that Hadoop sort of is on standby, so when I submit my job, it doesn't have to do any overhead, like any sort of ramp up, but we can just throw the code in and it runs right away. That is basically a way to do it, but you're getting into this sort of really top level or a few percentile of performance optimizations, which are really, really painful and hard to control. And this is not what Hadoop is designed for. If you look at the Hadoop code, it's all Java. I mean, who thought that Java can really like bring such a great advance? So everyone thought Java is, well, besides Java Enterprise, it's not really going anywhere. But it's really showing that it can be done, but you don't want to go further or lower than a certain batch rule. So real time often means, in this case, faster than batch. So you want to have something that you bridge the gap between this sort of 2 minutes or 5 minutes to even closer, or 3 hours down to 30 minutes, whatever the gap is that you're currently experiencing. If you're already down to 2 minutes with Hadoop, you're pretty good shape. But if you're down to like an hour, 3 hours, 4 hours, it would be nice to go down to a few minutes, right? So that's sort of the idea. Looking at someone like Facebook bringing down real-time statistics into 30 minutes, basically, into a 30-minute range with 600 million users, that's a huge effort. I mean, for a smaller company, going down to like a minute or two might be even more feasible. But I'm saying there is some sort of gap and you want to bridge it. The 80-20 rule, I think it still applies. Hadoop solves these 80% really easy. You just put Hadoop in, commodity hardware, all good, right? And you have this 20% only remaining to do the real-time thing, right? Like bridging the gap. And though typically these 20% take 80% of all your effort, and you still might not get to the end. So that's one of those, yeah, where it gets hairy. So try to get the go as close as possible, that's my advice, but don't overdo it. There is pain ahead, so be careful. What are the stopgap solutions? How can you bridge that sort of divide, that gap? We have seen lately, like just this week or last week, there's lots of blog posts showing up of people saying, oh, we can do that too. I mean, we have a product that can bridge that real-time gap. Whenever Facebook came out with that talking about real-time, and we're talking 30 minutes here, so it goes back to what I said before. For Facebook, real-time is 30 minutes. So go figure. It's like not real time. It's something close to good, very good, but there's room for improvement. So what can you do? You can do it in memory. You can do in-memory stuff. You can like use mem-phd, MemBase. Gigaspaces has a blog post out where they basically talk about you can use their Gigaspace product to bridge that gap as opposed to use HBase. I mean, why not? I mean, there's a lot of options. You have relational databases, you could add those and just basically have the database bridge that gap, so store some stuff. That basically brings you back to where you came from. We came from this LAMP stack, which had MySQL or Postgres SQL already behind it, and you already added memcached to make this faster for your clients. So this might not be the best option. So I'd say not good. Careful. Or NoSQL. NoSQL is like the buzzword of the year, I think, in the IT world, at least for me. And what could be Cassandra, HBase, Mongo, you name it, anything like even BerkeleyDB. BerkeleyDB is on its outset a NoSQL database. So anything you can think of could fill that gap. But I'm talking about HBase, obviously. This is why the talk is Hadoop and HBase for real time. Quick one. HBase, the architecture. Let's have a quick overview of how HBase works so you understand the implications to use HBase. And you can make a decision afterwards if you like it or not. It's not selling HBase, it's saying this is how HBase might work for you. And you can think of it and talk to me afterwards if you have questions. But yeah, that's basically my pitch. The architecture is we have an API on top. We have a master. It's also like similar to the name node in Hadoop, and we have the region servers similar to the data nodes in Hadoop or HDFS, which uses this H file underneath and the mem store to do the sort of like housekeeping. And it has this write-ahead log, which is similar to a bin log or binary log in MySQL. So it has a very similar feel to it compared to, say, a database. So it writes something into a log, so they can replay that log in case something goes wrong. Okay, and underneath we have HDFS, so it reuses a component that we already had in place. So this uses this is the file system. Great, you can rely on the file system. We know it's great. You can scale it and everything. So why not make use of it? And it uses Zookeeper, which is another Apache project, to do the coordination system. This runs in the background, don't worry about it. It's a great tool as well. But that's sort of the high-level API. Now, if you have to write against HBase, so you want to, for bridging that gap, you want to somehow make sure that your LAMP stack can talk to HBase. That's basically done through Thrift, basically here, Thrift client, REST client, Avro. So we start these servers on the HBase side. They could also reside, they can either reside within each region server. So each region server runs a Thrift server, or each region server starts a REST server or an Avro server. Or you can locate that one with your application. Just put it where the LAMP stack runs, where your application code runs. Put it there, like your PHP or Perl, and there's an interface for Thrift. You can compile into PHP and talk to HBase. So it's just like an API call. Just like store, get, delete, whatever you like. So that's basically the high-level overview. HBase is a good choice over normal databases because HBase has also scalability built in. That is something that databases often do not give you for free, or it comes as an afterthought, or it's really expensive. So HBase was designed, as Hadoop was, to scale from the start. And the way it does that, it's using this is like a logical table. You have like the rows A to S here, and it splits them into something called a region. The region is basically the element or the item of scalability in HBase. It's this auto-sharding of these rows into regions of a particular size, and these regions get then these are hosted by different region servers. You can see only one region server, like this region is hosted on this region server, say this one, and this is hosted by that one. But each region server hosts a number of regions. This is similar to continuous hashing and stuff like that, where you have a hash ring, you divide your space into subsets and give that subset a certain number of subsets to each server. HBase, though, instead of doing this premeditated, does this for you automatically. So all you have to do is just basically put data in, and it does all this balancing for you. It grows as you grow. So that's all done that way, and the client talks directly to the region servers to get the data. The distribution, though, is basically random. So you have a certain subset of keys on this server, there's another one here, another one here. So you do not really know where they are, these regions. They're just somewhere on the region server. So if you talk to it, the client resolves this for you. You don't have to know. You just say, give me row A. Row A, okay, fine. So it would go through here and say A, A is in this region, get it from here, fine. If this region server dies, the master is responsible to move these regions to other region servers, and there they are again. So you basically have never ever a problem of data like not being available, because this data, these sort of regions here, these rows, they are stored in HDFS, which we know is scalable and it's distributed. So all we have to do is basically have another region server take over, read the data from HDFS. It may have to replay the log file, but then it's done. What is important with HBase though is, so far that's okay. We have like regions somewhere, right? The key design is important. Whenever you write something on your application layer to use HBase to bridge this gap, you want to have HBase be as performant as possible. And to do that is you have to design the key right. The key is the row key, like just your main ID or whatever primary key in a database. You have to make sure that you distribute this well, because if you write sequential keys, you saw before, okay, the region that had the key, let's go back, this region here has A to C. If you write AAA, AAB, AAC, AAD, and so on and so forth, you know what? You're hitting this one server, this region. So this server, this poor server, out of your 100, has to do all the work. That's not good, because then you're down to one single server giving you all the performance. So your performance that you look at how many operations you can do per second is really like low. And it's like, what's going on? I thought the HBase does this sort of real-time thing, so it's fast. It's not, it can't do better, because if you do a design where you do sequential keys or random keys, these are the opposites. With the sequential reads, sequential keys, the performance, this Excel here, is low for writes. So you're writing really slow because you're hitting one region server. Though if you turn this around, just imagine you use MD5 to do you convert the key, the AAA, AAB into an MD5 hash. That hash is usually nicely distributed across the key space. You're basically hitting a random servers, and therefore you basically have a nice distribution, right? And in between is something where you can use sorted keys, or have something that's called promoted field keys. You can basically sort of tweak where you lie, but keep in mind when you use HBase, you have to use a certain key design to make sure you get the best performance. The cardinality is also important. In HBase, wherever you put your data, it defines how you can access the data. So make sure when you design the key that you can move the information that you need the most to the left. So the idea is that this is a coordinate of a data cell in HBase. So the first thing you have is the row key. Then you have the column family, you have the column qualifier. These are all like details of HBase. Just saying that as you design a key in HBase, make sure that you design it in a way that the data that you need the most, that you go by and search by and grab by and update and read and write, move this to the left, put this maybe in the key, like put your customer ID into the key, put your date into the key, but not as the first part of the key, because if you do a combined key and you put the date first, you have the same problem as before. You have sequential keys because dates are just going forward, right? So keep in mind these things. HBase has some sort of limitations, but if you design right, it works really nicely. Oh, we just skip this one. That's the same. So now we are using HBase and Hadoop for real time. So the idea is here that as you have the LAMP stack before, you have Hadoop, you add HBase. As easy as that, right? I said before, we're combining things, and that makes things work easier. So the combination there is great. So you keep the backup in HDFS, use MapReduce over HDFS to analyze the data, or over HBase if you want to, or you use direct access to HBase to put these data into HBase using a batched put, something that's an optimization, but instead of single-handedly writing data in, it's a good idea to batch them, or you do a bulk import. The bulk import is this line here. So from Hadoop, you can prepare data that goes into HBase. So this will preparing HBase to serve the data that you need to fill that gap. So you compute data in here that your front end, the report that we were talking about, to report how many streets we have in a certain vicinity, instead of going to MapReduce and waiting for a few minutes or an hour or two, you bridge the gap by putting HBase in that has the data readily available for you. So you have to do some logic somewhere that prepares the data, but the idea is you can bring it down by storing data here in this in HBase. Think of it as a database or data store. So this has random access. You can just grab something out of it and say, okay, that's what it is. You don't have to go on a huge file system and find out where things are or start a job to give you the results. You basically use that to get data right away. Or, that's another one, right? Here we add Flume. So Flume, before I had this, if I go back, so this was what I said, just combine the three. That's great, but how do you get the data from LAMP, from the web servers or so, or the application servers, into Hadoop? There's sort of like, you can copy, but it's a bit of a cumbersome way to get them in there, because Hadoop wants to have large files. But you don't want to collect like 10 gig of log files or so on your application servers all the time. You want to keep them lean. So to ship smaller updates, the solution for that one is Flume. You may know a similar solution from Facebook, which is called Scribe. Scribe does the same for Facebook, what Flume does for the Hadoop ecosystem. Okay, now that's great. Now you have data somewhere. You put all the data through HDFS directly into HBase and Hadoop. You can process that data, which is good. The problem here is you need to make sure that all of the data that you need that is detrimental to your business is very safe. So you have to make a decision if you want to have where the data is when something happens. And if HBase goes down, your real-time component, how do you recover from it? So that's like, you know that HBase, Hadoop and HDFS is very secure. So the idea is that we may have to somehow hold the data somewhere to recover from disaster, but also, it doesn't happen, just saying, but in case it happens. But say, we also want to do backups, right? The backups have a problem. All of the backups assume that HBase is running, and if it's crashed or down, how do you access the data to set up a new cluster to get back into production? So the next part is you add something that is this log processor. So you're basically going through, instead of talking directly to HBase for storing the data into it, you're going through this processor which does the actual log cleaning and stuff like that. That brings us to Facebook Insight. So Facebook Insight is a system where they track clicks on your like buttons. You put little components on your website, and as you basically put these components there and your users click on that, it gets tracked with your website saying that, oh, your users like your page 100 times or 1,000,000 times or whatever it is. It can be a lot. They have 1 million counter updates per second. I mean, that's quite astonishing. They tested this on a 100-node cluster, and so they do around 10,000 counter updates per second on an HBase node. So this runs on HBase. So the architecture is for them, they go through the LAMP stack, they go through Scribe, they go through something that's called P-tail, Puma into HBase. And if you look at, I'm trying to hurry up, you know. So if you look at this, what we mentioned before, Flume, right? But added this log aggregation. That's Scribe for Facebook. So they're adding something that grabs these logs from the web server and writes them securely onto HDFS. So they use Scribe. You could use Flume. Like you could use both actually. but Flume is available to you, so you can actually use that to rebuild the system. The filter layer, now you basically have to do something. In ptail, what they use with Scribe, it's actually following the logs. It's the typical tail that you know from your Unix or Linux operating system where you follow a log file, you do a tailf or whatever. That basically follows these files coming out of Scribe, and it separates them in different events. Again, this is internal, you can't use it, ptail, but you could use Flume. Flume has like little filter language that you can use to split up traffic. Next thing is the batching layer. They use Puma. I mentioned this. Puma is something that they aggregate batching in a batching fashion. A couple of updates. Here it's about a second. So it sounds quick or low, but for Facebook, with the number of updates they get, that's quite an amount of number. So they do this by a second. They then write this out into HBase from here. You could use something in the future. This like this gap that I see currently. You could use coprocessors in the next version that comes out in a few months of HBase to do the same thing. There's actually a Jira open that addresses this sort of thing, that to cache counters with coprocessors and batch them for update. And go figure who created that Jira issue. Not me. Someone from Facebook. So I think they know that they're on the right track here, right? So I'm saying I think that there's some merit to it. So they think it's going to work. So at least someone should work on it. Let's wrap this up. Yeah, you have to design for your use case. Do you want to be optimizing for read or write or both? Design the keys right. Typically, you design for write speeds because you have these many updates coming through from your website. So you design the keys so they're random. You write them into HBase and into HDFS, and use HDFS to do the batch processing, and use something like HBase to do to get the live counters out. In this case, we don't use values. In this case, you would use the counter feature that HBase offers. So you can actually increase these and just ask for, okay, how many hits did I have the last 10 minutes? And it would have that value readily available to you, as opposed to going through the logs and counting all the separate hits. This is basically giving you that stopgap to bridge into real time. Avoid hotspotting. This can happen on a region. I mentioned this before by key design, but it also happens sometimes on a table. If you have small tables and they're not distributed well, be careful to make sure that your distribution is matching your use case. And you have to sometimes manage your automatisms. This is an interesting one, but for HBase sometimes you have to switch off certain built-in features and manage them yourself. All of that is being discussed in many places, but yeah. One of the places where it's discussed is a great book from some guy that I know. So that's the book coming out in, I'd say, end of August, beginning of September. We're just going into production now, so we have, like O'Reilly has to print it, I think. So that's coming. And the interesting thing is, just to close the thing up, I decided not to shave and not to cut my hair until I'm done with the book, so that my family would see I wither and let me work on it, because I work from home mostly, and also have more time to finish it. And I was at Buzzwords where I looked the worst. This actually is trimmed and shaved and whatever. I cut my hair. But some guys saw me and thought it was so funny, so they came up with this version of the cover, which I thought was actually quite excellent, because I'm sort of like, I should probably, I think he meant that I'm the one in the front, I guess. And yeah, exactly. The horse will be me as well, I guess then. And I have my friends in the background helping me. These are the other committers or whatever you think, or the community helping bringing HBase to where it is. The book is also on the OFPS if you want to read it now. It's online. You can find it if you go to the Open Feedback Publishing System of O'Reilly. It's on there. Just search for OFPS and HBase and you find it. You give me feedback, find errors, mistakes. I'm loving it, because as I said, I'm just a developer writing a book, so I'm not free of faults. I'm happy to fix this for the next version at least. So I definitely read it, give me feedback. Right. And that's basically where I live as well, so just giving you an idea. So it's not all that bad, it's just the shaving and the hair cutting is bad. Any questions? Quick one, we have like how much?
With another session at the end. Final questions.
5 minutes. We have a few questions. Anyone has questions? Wow. Come on, you have questions, right? There's one. Thanks. Yes. Yes. So the question is if you can actually bulk import. Yes, that's the bulk import feature that I mentioned. So the bulk import feature creates the H files that HBase needs underneath. So you pre-create all the storage files, bypassing all the in-memory component and everything that HBase has in place, and creates the files, puts them into a staging area on HDFS, and then you issue a command which swaps them into place, making them available right away. So this putting into place is like just like the click of the button, basically. So you're done. The only time that you wait for it is the preparation of the file. You back to, and that's sort of like an interesting question, you back to batch processing. You prepare these files and put them into place, so you have to wait for them to be finished. So I think in the future there will be a combination of doing this batch processing and bulk import, but keeping the counters alive in the meantime. So you fix, say you have a machine learning algorithm which computes some sort of recommendation for you for what's happening on your website. Doing it only with the data in HBase, you might not be accurate, but it's enough to gap bridge the gap and stay current with a minor error rate, and then you use the hourly batch run to fix the model and put the right number into HBase. And then sort of, you see basically sort of like it drops off a little, comes back, drops off a little, but the customer possibly won't even notice, because if you go down to like a few error percentage, or like an error, like 1%, 2% error rate, it's pretty much on spot or on target anyways. Yes? So say again. Come from. I really can't hear, sorry.
Which rate tables by region load?
A region?
Region loads, like
divided. Oh no! If it divides it by load.
Yeah,
this is like. So the question was if HBase is smart enough to divide by load. Yeah, no, of course. So if it's now or in the future. Currently, the load balancing is quite simplistic. It only does it by number of regions per region server. So when you have a region server that starts up, it gets extra regions shifted over while others share or shed some load. What is missing is proper accounting. It's not only about the like how many requests a region gets, how much resources does it take on the operating system level, how much CPU, how much disk, and so that we aren't there yet. But it's definitely on the roadmap. Not sure when, but a lot of companies are interested that the HBase is smart enough so they can just put data in and it sort of shifts by load. Currently, no way. This is why all this exercise that I said there, design the keys right, is because of that. It's just, if that would be smart enough, you wouldn't have to do that. Currently you have. This is like an open source project. It just has its limitation. There was another question over there in the bike back.
You mentioned thrift.
Yes.
Yeah.
Oh, so the question is, if you go through an intermediate layer like Thrift or Avro or REST, I guess any of them, if that adds overhead, definitely. It adds overhead. If REST, for example, is good for few requests but larger ones, Thrift is good for more a higher frequency of updates. The idea with Thrift is that it's very lean in terms of protocol, but REST is quite noisy. The good thing with all of these servers is they keep a connection open and the table open to HBase. So it's better than doing this opening a connection to a table per request, but they certainly add a certain overhead. I know that Facebook uses Thrift, StumbleUpon uses Thrift. So they all are willing to take that hit. If you can bypass Thrift, if you can talk directly natively to it, that's the recommended way of doing it. Yeah, Java. It's only Java, it's the native one. There's also the new, it's also written in Java, but there's this async HBase client, which actually talks RPC protocol. If you were to take this and implement this in C, talking the same bytes protocol on the wire, you could have a C client, but no one has touched that topic because you're talking about RPC, and RPC is a brittle thing. But I'm saying natively support is Java, and it's anything on top of that, percentage-wise, I don't know, 10-15% performance penalty, not like 50% or so. It's just going slightly slower. Yeah. Okay, one more, sorry. This is where you...
Got the common salaries now.
Yeah, yes.
For the mail list, I've got that it's advisable to use as less number as possible. Expenditures only one.
Yeah.
Why
you're asking what sort of the limits are with the number of column families. Yeah, I know that the current advice is to keep it low. Again, we're back to the same sort of problem set where the question is why on the mailing list, why do developers or the other committers advise to keep the number of regions, number of column families low, There's a limitation currently in HBase that when you have something that is of mixed size, imagine two column families. One is called data and one is called meta. In data you put in web pages, which are say 10K each, just as an example. And you have the small one, meta, which puts in the language. So you're adding 10K here and 50 bytes here, 10K here, 50 bytes here. Once you hit the region size, or once you hit the in-memory size, the flush size, the system decides to flush all of the stores in memory across the entire region. So it saves a 64 megabyte file for the data column family and a 10K file for the meta column family. You're creating a lot of small files, which is already bad for HDFS. And then later on, these small files have to be rewritten, and as they're rewritten bigger in the background, adding these tiny small files to a large file, which takes a amount of time. So the IO churn that you create is just costly. Control, but at the moment advice to keep it small. If you have quite easy amount in each family, then you currently